Math at Work 10, this is your next lesson on just applying the Pythagorean Theorem. So in our last lesson, we looked at properties of right triangles, and we specifically looked at the Pythagorean Theorem being the relationship between the three sides, right, the legs and the hypotenuse. Okay, and we looked at how we can use that Pythagorean Theorem of a squared plus b squared equals c squared on how to find a missing side length, okay, whether that was the hypotenuse or one of the legs. What we're going to do in this lesson, no real new math. We're going to keep working with the Pythagorean Theorem. We're going to look at some other kind of context situations as where it might be used and how we can kind of use it in reverse to ensure that what we have is like a nice square corner and a nice right angle. Okay, so that's what we're going to be looking at today. All right, so again, what we've got is our knowledge of properties of right triangles, right? That knowledge of the Pythagorean Theorem and the relationships of those three sides. It can be actually quite advantageous in a lot of situations, right? So if a triangle meets the conditions of the Pythagorean Theorem, meaning that the two leg sides, if you square them and add them together, and it equals the square of the hypotenuse, that means you know you have to have a right angle triangle. So if you know that the Pythagorean Theorem is met, and you get a right triangle, that means you got a nice square corner. And square corners are obviously really important when it comes to construction. Okay, so oftentimes you'll see those tools, they have these triangle tools to ensure that things are squared up, right? Because that particular triangle is a Pythagorean triangle, right? A right triangle that meets Pythagorean theorem. Okay, so when we talk about those special types of triangles, right, those ones that meet the conditions of the Pythagorean theorem with whole number side lengths, right, so now we're talking about the weird decimal ones because you can't get those exact, but there are some where the side lengths are all nice whole numbers and they work out really nice and they still meet the Pythagorean theorem conditions. And those are called Pythagorean triples, okay, or sometimes Pythagorean triplets. Your most common Pythagorean triple is a 3, 4, 5 triangle. So that means your two legs are lengths 3 and 4, and then your hypotenuse would be 5, right? So you think about it, 3 squared is 9, 4 squared is 16. You add 9 and 16, you get 25, and what do you know, 5 squared is 25, right? So this is a nice Pythagorean triple. So as long as it's in this ratio, right, so any of its similar triangles to the 3, 4, 5, you get a perfect right triangle. Right, when I'm talking about similar triangles, right, I mean there's in these same proportions. So if you have that 3, 4, 5 and you multiply all of these values by 2, you get 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10, right? So a 6, 8, 10 triangle would also be a Pythagorean triple, right? Because 6 squared is 36, 8 squared is 64, add 36 and 64, you get 100, and what do you know, 10 squared is 100, right? So any similar triangle, meaning that the ratio is the same of those side lengths, you will be a Pythagorean triple. Another common Pythagorean triple is the 5, 12, 13, okay? It's just typically not used as much, though, because it looks just a bit funny, right, with one leg only being 5 and the other leg being over twice that length, right? Whereas this is kind of a nice, smaller, compact triangle. Okay, so as mentioned, when we talk about confirming the Pythagorean relationship, okay, we can kind of use it in two ways, right? We can use it forwards in the fact that, okay, if this is a right triangle, and I know it's a right triangle because I can see the little angle measurement in the triangle itself, then I can use the Pythagorean theorem to find the missing side length, right? And that was something we talked about last lesson. This theorem only gets to be used and only works if it's a right triangle. If you don't know that it has a right angle, you can't use this theorem. Okay, and we've just been using it to find those missing side lengths. Now, what's nice about it is that you can actually use the theorem in reverse, because if the Pythagorean theorem only works on right triangles, that means if the three side lengths of a triangle that you've been given fit that a squared plus b squared equals c squared formula, right, and it actually works out, that means you can then conclude, oh, well, if it fits the Pythagorean theorem with its side lengths, then you know that it has to be a right angle, right, and then that can ensure that you've got your shape has been squared up and you've got a nice right angle inside that shape, okay? So let's do that with an example, okay? So in this first one here, we're going to determine whether each of the triangles below is a right triangle, right, and we'll explain or we'll show our reasoning. So in this first one, in A, you've got this triangle that has leg lengths of 12 meters and 16 meters, and we see that it's what would be presumed to be the hypotenuse is 20 meters, okay? So, all right, so what we're trying to do here is confirm, right? So in that diagram, we don't see that that's a right angle. We don't know that it's a right triangle, but we can check to see if it is. So if we look at that, right, in that diagram there, okay, there's two ways we can do this, okay? One way is, and it's going to work all the time, is algebraically, right? Check. If this was a right angle triangle, then it would have to fit the a squared plus b squared equals c squared. And if this were a right triangle, the c value would have to be the longest side, right? And we have to do the 20 squared. And the thing is we're not sure if this is equal, right? So we're questioning, is one side going to equal the other? And if it does, then it's a right triangle. If it doesn't, then it's not, okay? So our legs would end up being 12 and 16. So we'd have 12 squared plus 16 squared. So 12 squared is 144. 16 squared is 256, and 20 squared is 400, right? And again, we're still questioning, are these two things equal? Right now, if we add 144 and 256, we get 400, right? And there you go. You get that 400 equals 400, so that means that this has to be a right triangle because the side lengths fit with Pythagorean theorem, okay? The other thing that you could do here is just a bit of logical reasoning, right? We talked about the aspect of a Pythagorean triple and all of its similar triangles and the ratio, right? So remember that main Pythagorean triple was a 3, 4, 5 triangle. And if you look at these numbers, 12, 16, and 20, you can actually take a look at that and say, well, wait a minute, these are all in the same proportions because 3 times 4 is 12, 4 times 4 is 16, and 5 times 4 is 20. So since a 12, 16, 20 triangle is a similar triangle, right? It's stretched by a factor of 4 from your known Pythagorean triple of 3, 4, 5, then therefore this is a right triangle. Okay? So sometimes you can always do it this way, but you can also try and do it with just a little bit of reasoning on similar triangles and knowing Pythagorean triples. Okay? So let's go back and take a look at that second example. Right? So in this one, we have a slightly different triangle given to us with our 3 side lengths. And they are 11 feet, 24 feet, and 27 feet. Okay, so 11 feet, 24 feet, and 27 feet. Okay? And we are questioning whether or not this is going to be a right triangle. So again, if it was a right triangle, the longest side would have to be C. Right, so we're going to be setting up that a squared plus b squared equals c squared. So the longest side would be the 27. And my two legs, a and b, would be 11 and 24. So you have 11 squared plus 24 squared, and we're basically saying, are these equal? Right? If they are equal, it's a right triangle. If they're not, it's not a right triangle. You don't have a right angle. So we can do 11 squared, we get 121. We can do 24 squared, we get 576. And on the right side, if we do 27 squared, we get 729. We add these two together, 121 plus 576, we get 697 is equal to 729. Which is obviously not true. 697 is not the same as 729. So because of that, this is not a right triangle. Right, it might be a little bit close, right? They're not too far off, but it doesn't work. This is not a right angle. It's some other angle, but not 90 degrees. Okay, so it's not a square. Like it wouldn't be a square nice corner. Okay? All right, moving on. Okay, so those are your answers again, same idea. So now let's kind of look at being able to apply that Pythagorean theorem, okay? So in this first example of applications here, George is making a rectangular picture frame. He wants to check that the frame has square corners. Calculate what the length of the diagonal must be for the frame to be square. Round your answer to the nearest inch, okay? So again, if you're trying to make it so that this is a squared shape, right, it's got square corners, you need to make sure that when you cut through the diagonal, right, and you've created these two separate triangles, that this length will, meet Pythagorean theorem standards, right? So if he's going to measure the diagonal to double check that, yes, I do in fact have I have square corners in my rectangular picture frame, we need to make sure that his measured diagonal matches with what we're going to calculate using Pythagorean theorem. Okay, so we're going to do that now. So 40 inches and 50 inches on our frame. All right, so you've got picture frame, right? That was 40 inches. This was 50 inches, and we are checking what that diagonal needs to be to ensure that that's a right angle. Okay, so what we would do again is, in order to have that as a right angle, it needs to meet Pythagorean theorem standards. So that would mean needing to do the Pythagorean theorem, right? So we're essentially solving for c, right? So a squared plus b squared equals c squared, right? A and b would be the legs. 40 squared plus 50 squared is equal to c squared. 40 squared would be 1600. 50 squared will be 2500. We add those two together, and we get 4100 is equal to c squared, and then we would need to square root that value in order to get the length of the diagonal, which is 64.03 inches, right? And I believe the question actually asked us for the round your answer to the nearest inch, so we would round that then to 64 inches, right? So that diagonal needs to be 64 inches. So when he measures it, it should be 64 inches, and if it's not, that means he doesn't have square corners, and he's going to have to readjust the sides of the frame in order to make it square. All right, so again, there's your answer in the notes as well. Okay. Okay, next thing, like I said, if we're trying to make something square, right, and we do the measurements and we know what it's supposed to be, but then when we measure it, it's not that, right, we need to then use that information in order to be able to fix it so that it is a right angle, or it does make a right triangle, right? So if you know what the measurements are supposed to be using Pythagorean theorem to get you your right triangle, and then when you actually do the measurements it doesn't work, that gives you that idea of, okay, well, how do I need to move something, right? Do I need to move it down? Do I need to move it over in order to get that length to be correct, right? So that's what we're going to look at in our next couple of examples, right? So if your measurements don't match, right? If your actual measurement doesn't match the hypothetical measurement that you should get using your Pythagorean theorem, you need to alter your object so that it does work, okay? So you can get, providing that what you're looking for is in fact a right angle, okay? So we'll look at this example here, okay? So in this one, Mick is the coach of a baseball team. He's measuring out a square baseball diamond in a field. The distance from one base to the next is supposed to be 20 meters. Mick has measured the distance between home plate and first base and the distance between first and second base, and they are both 20 meters. However, Mick thinks that something does not look right. He measures the distance between home plate and second base, and it's 30 meters. What's the distance between home plate and second base supposed to be, right, providing that it's a square baseball diamond, okay? Write your answer to the nearest hundredth of a meter. So we'll start with that one, right? So if we're thinking baseball, right, what you've got is home, first, second, third, and then back to home, right? And they're saying that this is supposed to be a square, and if it's a square, all the side lengths should be equal, and all of these should be right angles, okay? So it says that he's measured the distance from home to first, and it is in fact 20 meters. He's measured the distance from first to second, and it is again 20 meters, okay, or 20 meters, right? And, you know, if this was a right angle, right, he's measured this distance here and said that measurement is 30 meters. So let's check to see if those measurements actually work to make this a right triangle, right? Does the 20, 20, and 30 work in order for this to be a right triangle? So let's check, okay? I mean, if we just quickly go back to the question, right? It's saying, what's the distance between home plate and second base supposed to be? All right, so we're trying to figure out, okay, well, if it wasn't 30, what's it supposed to be? What is this distance of the hypotenuse, right, being directly across from the right angle? What's it supposed to be? So again, you set up your a squared plus b squared equals c squared from your Pythagorean theorem. 20 squared, right, these are your two legs, plus 20 squared equals some unknown. That's 400, that's 400. right? So 400 and 400 will make 800. That's equal to c squared. So to actually solve for the c, right, this distance between home and second, we would need to square root 800 to just get c by itself. And when we square root 800, we get a value of 28.3 meters. So the distance between home and second is supposed to be 28.3, but he's measured it as 30. So clearly it's not right? This is not a right angle in that case. Okay, so we've got our answer. We know that it's supposed to be 28.3. Oh, it says nearest hundredth, so that's 2 decimal places. So it's actually 28.28. We'll edit that on the board. All right, so it's 28.28 meters. And what's the problem? Right, so it's asking us now, what is the problem in this scenario? Well, the problem is that in order for that to be a right angle, right, in order for this to in fact be a square baseball diamond, this length should be 28.28, but it's actually 30, right? So what's happened is that, one of these bases is not shifted to the right angle. It's got the right distance, but it's not at the right angle, okay? And it's causing this to be too long, right? So what may have happened is that maybe this is still 20 meters, but it kind of got angled a little bit more this way, right? And now all of a sudden there's extra length there. Okay, so the problem is that that distance is too much, right? It's not been squared up. Okay, so part C says, how can Mick fix the problem? Well, how we're going to fix the problem is now we know that this is supposed to be 28.28 meters, so Mick can actually take his, whatever long measuring tape or turn the wheel or whatever he has to measure, go from home plate, measure out the 28.28 meters, tick it off and say, okay, this is where you're supposed to be base, and then adjust the base accordingly. Okay, so is just your fix that way. Okay, so it's the same thing if it was like that picture frame and you noticed it didn't work, right? It might just mean, okay, well, I need to angle this in a little bit more, right? Or angle it out if it was, not long enough. Okay, so that's just about being able to fix it. All right, and again, you see that answer in there as well, right, for A, showing you what it should be. And, right, so this they're saying is, obviously there's a distance of like 2 meters in the distance, right, so it's obviously not a 90-degree angle. He needs to bring the second base closer to home plate, and once he has it at the 28.28, he knows he's got he's got a right angle, okay? So again, no new real math here. It is just kind of still using the Pythagorean Theorem to be able to solve for missing side lengths, but then trying to apply it in the sense of, okay, well, does this work? Does it make a right angle? What can I do to fix it? Right, what types of situations will be coming on there, right? So I've got a worksheet ready for you, again, that just has like 5 or 6 questions selected from different spots in the textbook, and you can just practice those, and then of course email me if there's any questions with those, but again, you do have a solution set posted as well. Your next thing that I'm going to be posting is essentially like a Pythagorean Theorem check-in, right, where I will actually be emailing each of you. Sorry, no, that's my different class. What I'm going to be doing is just posting kind of like a little check-in kind of quiz on Google Classroom, mainly just multiple choice fill in the blank answers for you to kind of, check your knowledge on how are you with Pythagorean Theorem before we move on. Okay, so that'll get posted tomorrow on Friday, and then you can kind of chip away at it over the weekend and even on Tuesday, right, because it's a long weekend coming up, and then on Tuesday that will be due, and we'll start with new material then next Wednesday.